Hey guys, in this video we're going to talk about 2.1 through 2.3 in the textbook. In particular, we're going to talk about limits and how they relate to something called a derivative, okay? So, first thing we're going to talk about is slope, okay? So, everything that we're going to talk about in this unit and pretty much for half of the calculus class is going to be slope, okay? So in calculus, we are interested in the slope at a particular instant in time of a function. Now, in college algebra, you used to find the slopes of linear functions such as this, okay, a line, right? And so what was special about the slope of a linear function is that no matter where you are on the line, the slope is always going to be the same, okay? In other words, the steepness is the same throughout. Okay, so the steepness doesn't change. And steepness is just another word for slope. Okay. So in calculus, as I mentioned, we're interested in the slopes of nonlinear functions such as parabolas, like the one that is drawn here. And so the question is, how can we find the various slopes of nonlinear functions? Now, what do I mean by various slopes? Well, the slope is always changing, right? If we start at time equals 0 and we just move up, what's happening to the slopes of these lines that touch the curve is that at t equals 0, the slope starts out positive and fairly steep, and then it starts to flatten out, right? It starts to flatten out, getting very flat at the top, almost a slope of 0, and then it starts to go negative, right? So right here it starts to go negative until we reach t equals 6. Okay, so this is going to be positive. So the slope's constantly changing here. And we're going to use calculus to actually figure out what is the slope at an instant of time. For example, what is the slope of this curve when time equals 3 seconds? And what does that even mean? Okay. So the first thing we're going to talk about is approximating the slope at a point. And so the first definition we need is average velocity. So velocity is just the same thing as speed, but with direction. So, if you say something like, I'm driving 40 miles per hour, we have no idea if you're driving backwards or forwards. Whereas with velocity, if you say you're driving negative 40 miles per hour, well, we know that you're driving backwards because velocity has direction. So when we have a position versus time graph, such as this guy, position is on the y-axis, which is in feet, and time is on the x-axis. When we have that, since velocity is the change in distance over the change in time, this is velocity, right? Since that is equal to velocity, we can figure out the slope. The average velocity is just the slope of the line defined by two endpoints. Okay. So the first example, what is the velocity of the golf ball from 2 seconds to 5 seconds? So we go to x equals 2, and I'm just going to sort of draw a little dotted line up here. We're not sure what that y value is, but we're going to figure it out soon. So that's my first endpoint. My second endpoint is at 5 seconds. So on the curve, it looks like 5 seconds is about right here. Okay, so I'm trying to figure out the slope of this line, okay? And it's not exactly drawn to scale, but maybe we can make it a little bit more accurate. Maybe it's more like that. So we're trying to figure out what the slope of this line is. Now, slope if you recall from your algebra class, is y2 minus y1 over x2 minus x1. Well, in order to plug this into the slope formula, we actually need points. Okay, so this first point has an x value of 2, and the y value is f of 2. Whereas the second point right here has an x value of 5 and a y value of f of 5. Okay, so y minus y over x minus x. So our slope formula turns into y minus y over x minus x. Okay, now what's f of 5 and f of 2? Well, we need to actually use our function rule to get those values. So the first one, f of 5, if I plug in 5 in for x into my function, let's see what I get. Okay, let's just get the calculator out. All right, so f of 5 is 100. So I can just replace that here with 100. And then f of 2, I do the same thing. I'm just plugging in 2 in for x into my function rule. Okay, so negative 16 times 4 plus 200. And that's going to give me 136. So that can go there. Then I just compute it. 100 minus 136 divided by 5 minus 2. And I get negative 12. Now, what are my units? Well, velocity is distance over time. And so my units on top is my distance, which is given by the y value. So it's going to be feet. And then on the bottom is time. And my unit for time is seconds. So this is going to be negative 12 feet per second is the average velocity between these 2 points. Okay, let's do another example. So what is the average velocity between 3 and 4 seconds? Okay, so this time we have 3, and then we have 4, maybe like right here. And we want to find the slope of this little segment right here. So again, we do the same thing. We write our x and our y value. So our x value is 3, our y value is f of 3 for that first point. And then over here, we have 4 comma f of 4 is our second point. And so our slope formula tells me I want to do y minus y over x minus x. And so f of 4, let's do that over here. It's negative 16 times 4 squared plus 100 times 4. Okay, so what is that going to be? 16 plus 400, so that's going to be 144. So that's 144, and then f of 3, I'll do over here. Okay, so I'm getting 156. All right, so evaluating this, 144 minus 156 divided by 1. So that, again, we are getting negative 12 feet per second for the average velocity between 3 and 4. Okay, so, all right, we just established average velocity is slope, and so I'm going to give you a formula for average velocity and a picture, okay, to show you kind of, what I mean by this, okay? So if we're given a function f of x, okay, and you'll see why we're defining it this way in just a little bit. Let's say that our first point, right, on our function right here, let's say that first point is f of x, And of course, the x value is x, and so my ordered pair is x comma f of x for this first point. My second point lives up here, and it is h away from x in the horizontal distance, as we can see here. What is h? We'll talk about that in a moment. But you can see that the x value here is x plus h, and the y value, the corresponding y value, is f of x plus h. Therefore, if we use our slope formula with these 2 points, y minus y over x minus x, well, these x's cancel out and we end up getting this in orange. Okay, so that is going to be our average velocity. Hey guys, in the last video we talked about the average velocity between 2 points, namely the points x comma f of x and f of x plus h comma f of x plus h. And so we got the slope formula right here, that's the average velocity. And I want you to look at this formula while we're talking about the next slide and see what this formula has in common with the formula for instantaneous velocity, which is what we're really interested in, the velocity at a point. Okay, so the instantaneous velocity at a point, x comma f of x, is this. Okay, so basically it's just the average velocity, but the limit as h goes to 0 of the average velocity. What does that mean? Okay, we're going to talk about what that means, but basically what the instantaneous velocity is just the slope of the line tangent to x comma f of x. So again, that's that red line that you see in the picture. This is the instantaneous velocity. All right, so now I want you to look at this, and now we're going to do a visual demonstration on Desmos. Okay. All right, so I have pictured 2 points. The green point is x comma f of x. The purple point is x plus h comma f of x plus h. Now, again, we can find the slope or the average velocity by using the formula in the orange box that we talked about. But we are interested in the slope at exactly that green point. And how do we do it? Well, we have to make sure that those points are very close together, because right now, that estimate is not going to be a good estimate of the slope at the green point, right? This one, though, might be a little bit better of an estimate, right? This one, that's an even better estimate of the slope of the tangent line at the green point. An even better estimate. You see how the line starts to look tangent? It looks like it's just touching the green point. Whereas up here, we have a secant line. We have a line that goes through 2 points. But that's no good, okay? We want to get really close. And what does really close mean? Well, it means that we're taking the limit as h goes to 0, okay? In other words, as this triangle gets really small, h is going to 0, and we are approaching the tangent line right here, okay? So, yeah, that's a little visual representation of instantaneous velocity. Pretty cool, if you ask me. Okay, so I mentioned these definitions in passing, but here they are for your notes. The average velocity between 2 points is just the slope of the secant line that goes through them. In other words, we have the slope of the secant line. Secant lines go through 2 points on a curve. The instantaneous velocity, on the other hand, is the slope of the tangent line of the curve. So tangent lines only touch the curve at 1 point, namely the point we're interested in. So the question is, how can we use average velocities to estimate instantaneous velocities? The answer is make h very small, like we had on the demonstration. So like, you know, this is when h is pretty big, right? X and x plus h are pretty far away from each other. But as h gets smaller, this point gets closer to x. So the idea is to make h super small to give a good estimate. So we're going to do two estimates, and we're interested in what happens at x equals 3. The first thing I should mention is that the function that we see here is x squared minus 5, because we're going to have to like use that to find the points. Yeah. So that's the function of this curve. Now, it says when h equals 0.1, what is the average velocity between 3 and 3 plus h? Okay? So the first thing, when here is x is 3, right here is purple. So let's say the purple point, x equals 3, and maybe I'll do the green point as 3 plus h. So 3 plus h in this case, if h is 0.1, x is going to be 3.1, right? 3 plus 0.1. And so that is going to be very close, right? There it is. So this guy is going to be at x equals 3.1. And the question is, what is the slope? What is the slope of that little segment right there? And as h gets smaller and smaller, those points are going to get so close together, I'm not even going to be able to draw them anymore. Okay? So let's first estimate our first thing. So we have x equals 3, and we have f of x equals 3 squared minus 5, which is 4. All right, so that's 1 point. 3 and 4. And our second point, x plus h, we have 3.1. F of 3.1 is going to be 3.1 squared minus 5. Let's see what it is. 4.61. So this is 3.1 comma 4.61. So those are the points that we have. This guy's my purple point. This guy is my green point. And now let's find the slope. Let's find the average velocity. So the average velocity, we have y minus y over x minus x. Let's see what that gives us. All right, we get 6.1. So that is our first estimate. Our first estimate is the slope of the tangent line at x equals 3. It was kind of close to 6.1. Let's make it closer. How do we make the estimate closer? We make h even smaller, right? We make h even smaller. So let's say we have our same first point. Okay, so this guy is the same. We have 3 comma 4. How about we make h, instead of 0.1, let's make it 0.0001. That's pretty tiny. Well, kind of. So if h equals that, then x is 3 plus that. So in this case, x is going to be 3.0001, and f of 3.001, just plug it into the function. 3.001 squared minus 5 is going to give us, dun, 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 okay, so this is going to give us 4.006001. All right. So this time my green point becomes 3.001, 4.006001. And now we find the average velocity between these 2 points. Okay, y minus y over x minus x. Let's see what the calculator gives us here. Okay, I get 6.001. So as h goes to 0, what do you think the velocity is going to? Well, it looks like it's going to 6, right? Because this is an okay estimate. This is an even better estimate. And my hunch is that as h gets smaller and smaller, this thing is going to get closer and closer to 6. Okay, how do we verify this? How do we verify this? So I'm going to clear this off. And maybe, let's see. Yeah, okay, so we do this in the next slide. We're going to verify that it indeed equals 6. So first of all, we need our function. Our function was f of x equals x squared minus 5. And we need our instantaneous rate of change / velocity definition, which is the limit as h goes to 0 of f of x plus h minus f of x all over h. Now we need to actually compute this and make sure that we get 6 as an answer. Okay, so we were interested when x equals 3, right? So we are trying to find the instantaneous velocity at x equals 3. So we need to plug in 3 in for x into our limit, into our function for instantaneous velocity. Okay, so let's do that. So we have f of 3 plus h minus f of 3 over h. Now I'll do this over here. What is f of 3 plus h? Maybe I'll do it a little bit lower. So what is f of 3 plus h? Well, all we're doing is plugging in 3 plus h into our function. So we have 3 plus h squared minus 5. Okay. And then f of 3, I'm just plugging in 3 in for x into my function. So I get 3 squared minus 5, which is just, let's see, 4. Okay. All right, so I'm going to plug in 4, and I'm going to plug in this into my equation up here. So the limit as h goes to 0, well, we just found f of 3 plus h is the same thing as 3 plus h squared minus 5, minus, we just found that f of 3 was equal to 4, so minus 4 all over h. And now this is where the fun starts. Okay, so now we can clean up the top by foiling. 3 plus h squared is the same thing as 3 plus h times 3 plus h. Let's FOIL this guy out. First, outer, inner, last. Combine like terms to get 3 plus h squared is the same thing as 9 plus 6h plus h squared. All right, so I'm going to substitute that here. So this is the same thing as 9 plus 6h plus h squared. Okay. And then I had that minus 5, minus 4, which I'm just going to make into minus 9. Why not? Okay, so there's the top. There's the bottom. Can't forget my limit. Okay, I'm going to erase some of this to make some more room. All right, now I can combine like terms on top. These 9s actually cancel out. And I need to now factor the top, because at this stage you still can't plug in 0 for h because you're going to have an undefined denominator. However, if we factor an h out in the top, what's going to happen? Haha, these h's cancel out, and now we're golden. Right? Because now we can plug in 0 for h. Oh my gosh, did we get it correct? Yes, we got 6. Okay, so the instantaneous velocity, the slope of this tangent line is equal to 6. Does it make sense? Yes, it's a positive slope, certainly. And our estimate was, we did a pretty good job with our hypothesis. So yeah, that's how you do it. Should we do another example? Let's see. Yeah, why not? Okay, so here's some notes. Now I've been talking about position versus time function and average velocity and instantaneous velocity in terms of slope. But we don't have to always talk about position versus time functions. We can just talk about general functions. And instead of saying average velocity, we just say average rate of change or average slope. Either one will work. And instead of saying instantaneous velocity, we just say instantaneous rate of change. And now here is the new word. Another word for instantaneous rate of change is the derivative, okay? We are going to spend basically more than half of this semester looking at the derivative, okay? So it's very, very important concept in calculus. And you guys aren't going to like me a little bit later because I'm going to show you some shortcuts of how to find the derivative quick without these limits, but you know, it's a good exercise to do these problems with limits. So anyway, the derivative is the instantaneous rate of change, aka the slope of the tangent line to a point. Okay, and the way that we write the derivative is kind of important. We say the derivative of f at a point x is written like this. And we say this is f prime of x, okay? So f prime of x, that's how we pronounce that. And it's the same thing that we had before for instantaneous velocity. It's the same exact definition, but we can use it interchangeably with f prime of x. That's our derivative. Now, if the limit exists, such as in this example, the limit did exist and it equaled 6. If the limit exists, then we say that at this point, the function is differentiable. Okay, we're going to talk more about what that means a couple of lectures from now, but that's the general idea. Okay, so here we go. Let's do some more problems with the limit. So find the derivative. Okay, so again, derivative is just this limit definition that gives us instantaneous rate of change. So the derivative is just the limit as h goes to 0 of f of x plus h minus f of x all over h. And we're given f of x, which is cool. And we're also given x, which is nice. Okay. Oh, and then we want to find out this x as well. I think I'm going to finish this example and then do the rest of these in a separate video. But let's go ahead and knock this out. All right, so f of x plus h. Let's do this off to the side here because I want to just figure out what that is. So again, I'm just plugging in x plus h into my variable x in my function. And I just get this. And then f of x is just 5x squared. Oops. So I can plug these values into my limit definition now. Let's do it. Okay, let's simplify the top. So again, I'm going to leave that 5 in the front and just FOIL this this x plus h squared. So this is right here. First, outer, inner, last. I have 5 times first, outer, inner last. Combine like terms to give me 5 times x squared plus 2xh plus h squared, and then I can distribute that 5. 5x squared plus 10xh plus 5h squared. Okay, so I can replace what I have in this first little part with what I just found. Let's do it. And then I have this minus 5x squared all over h. Okay. I have some things that'll cancel. These are going to cancel. That's pretty much it. Okay. Let me erase this, make some room. Okay. So now what can I do? I can factor out an h on the top. It's always very satisfying to factor out an h. So we have 10x plus 5h. That's how that goes. And then these guys go away. Now, I am trying to figure out the derivative at x equals 1. So instead of doing it, like, I could have plugged in 1 from the get-go, but you can do it at the end too. It's no problem. So I'm going to do that. So if I plug in 1 for x, let's just write this right here, x equals 1. If I plug in 1 for x, I get limit, h goes to 0, 10 times 1 plus 5h. Of course, 10 times 1 is 10. And now I just have to plug in 0 for h. And so that is going to give us 10. Okay, so what did I just find? I found, okay, therefore, let's write it out in words. Therefore, the slope of the line tangent to x equals 1 is 10. Okay, so let's scroll up here. X equals 1 is maybe right here. And so the slope of this tangent line is going to be 10. All right, now let's look at x equals 1/2. Do you expect this to be a steeper or a flatter slope? Let's find out. Okay, so when x is 1/2, well, I can just use, I can backtrack. So, like, I'm going to just erase this. I'm going to erase this, and we're going to say, instead of x equals 1, let's try it at 1/2. Okay, so now I'm just plugging in 1/2 in for x to give me 10 times 1/2 is just 5. So we have limit as h goes to 0 of 5 plus 5h, plug in 0 for h, and we end up getting 5. So, therefore, let's write in words, the slope of the line tangent to x equals 1/2 is 5. Okay, does that make sense? Well, let's see. 1/2, that's going to be about right here. So that's our slope. And I think that does make sense, because doesn't the slope of this line look flatter than the slope of that line? Hence, the slope is a smaller positive number, and so it's flatter. Yeah, so anyway, that's that example. I think I'm going to hold out until the next video to work this example, but thanks so much for watching, and I'll see you guys in the next part. Hey guys, in the last video we left off with this example, and so we are finding the derivatives of functions at certain points. In other words, we're finding the slope of the tangent line at points. And in this case, we have this function f of x equals square root of x plus 1. And that's shown in this graph right here, this function. And we're trying to figure out what is the slope of the tangent line at x equals 3. So right here is where x equals 3. We want to figure out the slope of this line right here. And to do that, we need the limit definition of a derivative. And that tells us that the limit as h goes to 0 of f of x plus h minus f of x divided by h. Okay, so we need to evaluate this. All right, so f of x plus h, well, I'm just plugging in x plus h in for x into my function. And so what I get is x plus h plus 1 under the radical. And then f of x, of course, is just our function that is given, which is the square root of x plus 1. And so I can just plug in what I have. I have the limit as h goes to 0 of the square root of x plus h plus 1, all under the radical, minus square root of x plus 1. And that is going to be over h. Okay? So at this point, we can't really do anything to the numerator. We can't simplify or combine like terms. And if we try to plug in h now, we're still going to get an undefined denominator. So the strategy that you can use when you have radicals is multiplying by the conjugate. So remember, multiplying by the conjugate is we're basically going to be multiplying by the numerator, except we're changing the sign. Okay, so instead of multiplying by a negative, we're going to be multiplying by the numerator, but a positive version. Okay, so I'm going to do, remember I have to multiply top and bottom by the same thing. So I'm going to multiply top and bottom by the same thing, except we have a plus in the middle. Okay. So minus 1 divided by square root of x plus h plus 1 plus, okay, this is a plus sign, x plus 1. Okay. Okay, so I want to go ahead and FOIL the top. Right, and so first, if I multiply these guys together, it just cancels out the radical. So let's write that down here. I just have x plus h plus 1, and I multiply the first terms. Okay. Now if I do my outer terms, root x plus h plus 1 times root x plus 1, that doesn't cancel anything because it's not the same thing under the radical, so it's just kind of a big mess. But notice that with our inner terms, we're multiplying the same exact thing as our outer, except we have a negative version. And so the outer and the inner are going to end up canceling each other out, and so I'm just not even going to write that. Okay, so those are going to cancel each other out. And then finally, my last, if I do negative root x plus 1 times positive root x plus 1, well, since it's the same thing under the radical cancels, and I'm just left with negative x plus 1. Okay, and I still have this is over h times root x plus h plus 1 plus root x plus 1. Okay. All right, so I can combine like terms in the numerator. And so those x's are going to cancel out as well as the 1's. And so I'm just left with h over h root x plus h plus 1 plus root x plus 1. And those h's are going to cancel out to just leave me with 1 over root x plus h plus 1 plus root x plus 1. And so now what I want to do to find my derivative is I want to, remember, I'm taking the limit as h goes to 0. And now once I plug in 0 in the denominator, there's no problems. It's not going to be an undefined value. So let's plug in 0 for h into my denominator, and I get just x plus 0 plus 1, which is just root x plus 1 plus root x plus 1. Okay, when I plug in 0 for h, and then I can combine the bottom, that's 1 of something plus another is 2 of that something. So this becomes 1 over 2 root x plus 1. So that's my derivative. And I'm interested in finding the slope when x equals 3. So I need to plug in 3 for x to figure out what the slope is. Okay, so I end up getting 1 over 2 times root 4, which ends up being 1 over 4 is my slope. All right, so therefore the slope is 1 over 4 at x equals 3. And does that make sense from our picture? Well, we know that it's a positive slope for sure. And so yeah, that makes sense. Our slope's 1 over 4. Okay, let's do another example. Okay, so now we have f of x equals 1 over x squared, and we're interested in finding the slope when x equals 4. So that's going to be right here when x equals 4. It looks like a pretty flat slope. What is the slope? Okay, so again, we need to use our limit definition of a derivative. Maybe I'll shrink this picture a little bit. Let's see if I can do that. Okay. So our definition is limit as h goes to 0 of f of x plus h minus f of x over h. And let's do this over to the side. F of x plus h. We're just plugging in x plus h into 1 over x squared in for x. So this is 1 over x plus h squared. And then, of course, f of x is just what we're given, which is 1 over x squared. Okay. Okay, so let's plug in what we have. So we have 1 over x plus h squared minus 1 over x squared over h. Okay. So again, we can't plug in 0 right now for h because then we would get an undefined denominator. So really the one thing that we can do with the numerator, we don't have radicals, so it's not a good idea to multiply by the conjugate. But we can subtract the numerator by getting a common denominator. And so let's go ahead and do that. That's really the only thing we can do at this point. Let me do that off to the side, maybe over here. So I have 1 over x plus h squared minus 1 over x squared. And so to find the common denominator, in this case, I just multiply those denominators together to give me x squared times x plus h squared. That's my common denominator. And let's see, x plus h squared. And so with my top function right here, I have to multiply the denominator by x squared on top and bottom. And so I get x squared here. On the second one, I have to multiply the numerator and the denominator by x plus h squared. Okay, and so this becomes negative x plus h squared. And now I can combine the numerator and the denominator. So let's go ahead and just replace what we have currently with what we just found. So this is going to be x squared minus x plus h squared over that common denominator, which is x squared times x plus h squared all over h. Okay. Okay, so what can we do at this point? Well, we could, what we could do is we could expand the x plus h's. Really, we can't do anything else at this point. So I guess we can go ahead and do that. The x plus h squared. So what we have, x plus h squared is the same thing as x plus h times x plus h. First, x squared outer plus xh inner plus xh, and last plus h squared. So x plus h squared is the same thing as x squared plus 2xh plus h squared. So I can replace that wherever I see an x plus h squared to see if anything is going to cancel out. So I have the limit as h goes to 0 of x squared minus x squared plus 2xh plus h squared, all divided by x squared times x squared plus 2xh plus h squared, all divided by h. Okay, so this kind of looks like a mess, but that's okay. Let's go ahead and erase some stuff so we have more room. Okay. Now I can distribute that minus sign, and let's see, what can I do from here? Yeah, I could. I'm not gonna distribute the bottom. Let's see if anything cancels out. So on top, I get x squared minus x squared. That cancels out. Right? I have x squared minus 2xh minus h squared, right, when I do the distributing. So those x squareds cancel out, and I'm just left with 2xh minus h squared over x squared times x squared plus 2xh plus h squared, and that's all over h, which I'm just going to write as times 1 over h, okay? So it's the same thing as writing that whole thing over h. All right, so the whole goal is to kind of get an h to cancel out. Okay, and that's what's going to happen, because look at the numerator. We can pull out an h. So let's do that. So if we pull out an h, okay, we're left with this. And so these h's can divide each other out, right? And now we're in a good position because we don't have a 0 in the denominator when we plug in 0 for h. So let's go ahead at this stage and plug in 0 wherever we see an h. Okay, so when I do that, I get negative 2x on top. That minus 0 is just nothing. And then I get on the bottom x squared times x squared. That's it, because the 2xh goes to 0, the h squared goes to 0. Okay, and so that's what I get. And then I can even further simplify this if I want to by canceling out an x on top and bottom. And so my derivative is just negative 2 over x to the third. All right. And so I'm interested in the slope. Let's go back up here. When x is equal to 4. Okay, so when x is equal to 4, let's see what our slope is. Okay, so 4 to the third. Let's see, remind myself what that is. Okay, so we have negative 2 over 64, and that is going to reduce to negative 1 over 32. That's my slope. Okay, so this is going to be, our answer is negative 1 over 32. That's the slope of this tangent line right here. All right. You might have something on your homework that says find the derivative by using the difference quotient. The difference quotient is just the limit definition of the derivative. And notice that it's not asking us to actually find the derivative at a point, so we just want to find it in general. Okay, so our function is 3x squared plus 8x, and we're going to use our limit definition as h goes to 0 of f of x plus h minus f of x all over h. Now f of x plus h, I'm just plugging in x plus h anywhere I see an x. So this is limit as h goes to 0 of 3 times x plus h squared plus 8 times x plus h. And then I'm subtracting f of x, which is just 3x squared plus 8x all over h. Okay. So let's clean up the numerator a little bit. Let's go ahead and distribute the x plus h's. Well, again, x plus h squared, we do that off to the side. We get x squared plus 2xh plus h squared. Okay, so I get limit as h goes to 0 of 3 times x squared plus 2xh plus h squared, plus, if I distribute this 8, I get 8x plus 8h, distribute this minus 3x squared minus 8x, all divided by h. All right, let's go ahead and distribute this 3 in here. Let's go ahead and do that. So we have limit as h goes to 0 of 3x squared plus 6xh plus 3h squared. And then we have all of this stuff after it. And we're going to have some things that cancel, I'm sure. So these 8x's cancel. What else cancels? The 3x squareds are going to cancel. And that looks to be about it. But notice at this point we can factor out an h in the numerator. So if I factor out an h, I'm left with 6x plus 3h plus 8 all over h. These h's cancel out, and the last thing to do is to plug in 0 for h. So my answer is the derivative of that function that we were originally given is just going to be 6x plus 8. And that is our answer. Now, if you were trying to find the derivative at a point, you would just plug in whatever that x value is to actually get the slope of that tangent line. But here they're just asking for the derivative in general. Okay, so now we have this question, rank in order from least to greatest f prime of x1, f prime of x2, and so forth until x4. And then they say which x values appear to have a slope of 0. So let's go ahead and rank these first. Okay, so remember, f prime means the derivative. The derivative means the slope of the tangent line. So at x1, if we go up like this, it's about right here. And so the slope of the tangent line is going to be negative for sure. And so we'll just kind of draw a picture to get a visual there. Looks pretty steep in the negative direction. Let's do f prime of x2. So x2 is right here, and so my tangent line looks to be positive. F prime of x3 is going to be right here. There's my tangent line to x3. And finally, let's do purple for x4. So x4 is kind of not even really on the page. It's somewhere up here, but that's going to have a pretty positive, a pretty steep positive slope. Okay, so from least to greatest, which has the smallest slope? That's going to be the steepest negative slope, which appears to be the red one. Okay, so f of x1 is the smallest. Do we have any other negative slopes? Yes, we do. We have this guy as a negative slope. And so that's going to come next because it's the only other negative slope. So let's do that. And then positive slope, the flattest one is going to be the smaller of the positives, which is this one. Okay, so that is going to be f prime of x2. And the largest slope is going to be this positive, very steep slope, which is f prime of x4. Okay, and it says, which x values appear to have a slope of 0? Let's go ahead and clear this out. Well, let's see. So a slope of 0 is going to be a horizontal line, right? And so that is going to happen sort of at these peaks. We have these horizontal lines, okay? So all of these x values appear to have an instantaneous rate of change of 0. And we can't really list out what these x values are because a lot of them are fractional values. But the idea here is wherever we see this flatness is where we're going to have a slope of 0. Okay. All right, so let's go ahead and do a word problem using derivatives. Okay, so they tell us that the position of an object moving in a straight line is given by this function here. So this is a position versus time function where t is measured in seconds. First question says, what is the average velocity between 0 and 2? Remember, average velocity is just the slope. Okay, so in this case, we're just doing f of 2 minus f of 0 over 2 minus 0. Okay, so that's just our slope. And so f of 2, if we plug 2 into our function, we get 4 times 2 squared plus 3 times 2 plus 14. Let's see what that gives us. Okay, so that's going to give us 36. And then f of 0 is going to give us 14 when we plug in 0 for t. Okay, so our slope, our average velocity, is going to be 36 minus 14 over 2 minus 0. Okay, so that's going to give us 11. And our units for velocity is distance over time. So the distance is going to be in meters, and our time is given in seconds. So this is 11 meters per second is our average velocity. Okay, let's look at the next question. It says, what is the equation of the instantaneous velocity of a particle at time t? So instantaneous velocity means the derivative. That means we need to use the limit function. Okay, so f of x plus h, we're just plugging in well, instead of x, we're plugging in t because that's our independent variable here. So we're plugging in t plus h anywhere we see a t. So maybe I'll even like adjust the definition here. Let's do that. So we have f of t plus h minus f of t over h. Okay, so t plus h, well, let's see, 4 times t plus h squared plus 3 times t plus h plus 14 minus f of t, which is just the function, and that is all over h. All right, so let's go ahead and expand this out. Okay, so t plus h squared is just t plus h times t plus h. So I get t squared plus 2th plus h squared. All right, so this becomes 4 times t squared plus 2th plus h squared, plus distributing this 3t plus 3h plus 14. Make some room here. Okay, so maybe I'll have to do it on the next line. Minus 4t squared minus 3t. I'm distributing this negative sign. Minus 14 all over h. Okay, so I am seeing some things that are canceling out. I see these 3t's cancel out. I see the 14's cancel out. I see, let's write it over here. So if I distribute this 4 in here, I get 4t squared plus 8th plus 4h squared minus 4, no, let's do plus this 3h minus 4t squared. And that's all over h. Okay, so I'm going to erase this. Okay. All right, so these 4t squares are going to cancel. And then at this point, I can pull out an h in the numerator. So if I pull out an h, I'm left with 8t plus 4h plus 3 all over h. Those h's cancel. And if I set, at this point, I can plug in 0 for h. And so my derivative is going to be 8t plus 3. Okay, so that's my instantaneous velocity. Okay, so there it is. So which t value is the instantaneous velocity equal to 27 meters per second? So we just found the instantaneous velocity. The instantaneous velocity is 8t plus 3. So we need to set up our equation the following way. We have 27 is equal to 8t plus 3. Right? Our instantaneous velocity is given by that equation, 8t plus 3. And now we need to solve for time. So if I subtract 3 from both sides, we get 24 equals 8t. Divide both sides by 8, and I get t equals 3 seconds. Okay, so at 3 seconds, my instantaneous velocity is 27 meters per second. Okay, the next one says, what is the instantaneous velocity at t equals 6? Okay, so that's just, we have a formula for instantaneous velocity as found in part B. So we have instantaneous velocity is equal to 8 times the time plus 3. And so all I have to do is plug in 6 here to get, what is that going to be? We have 51. So instantaneous velocity at 6 seconds is going to be 51 meters per second. And I think that is the last part of this lecture. So I hope you guys enjoyed the video, and I'll see you guys next time. Thanks for watching.